We currently have 12 labs that develop. They're mostly across the US. There's one in Israel. Laura Furman, I don't know if I emailed you guys this. She's teaching a 2-week course in Israel on Rosetta, if you guys want to go. But she's the only one outside of the US that develops Rosetta. The rest is here in the United States. Jens will actually show you a picture of where it's all developed and who are the major figures. I'm going to kind of brag a little bit about Rosetta because I think it's a very powerful software suite. We were the first software suite to create a new protein computationally. That's top 7. We were the first to create an enzyme computationally, purely computationally. That was the Kent elimination. And we were the first to create a molecular switch, and I forgot to put it on my slide what that was. Sorry about that. And every 2 years, we're in the top 5 of CASP, and CASP is simply a folding competition. And we always score in the top 5. For a while, we were number 1, but some people have started to beat us. That's fine, because we have other things going for us. Oh. Extra long. It's very good.
Don't worry about it.
Okay. So, why is Rosetta so successful? I'm sorry, I can't talk.
Hey Sam, let's go under this one too.
Well, can we just later on? So why is Rosetta successful? Why have we been able to accomplish so much? There we go. And really, the reason why we're able to accomplish so much is because we have robust conformational sampling, and we have a very nice scoring function. And whenever I talk about conformational sampling, I talk about, what I mean is on the global scale. So if you look at this video, you can see loops changing, secondary structure changing. All of this is happening in the Rosetta application whenever you design when you relax the protein, design the protein, dock the protein. This global conformation change, the protein changes. It's all done through multi-cartline. And not only that, we sample side chain conformation. So more on the local setting, we are actually changing the conformations of amino acids by swapping in and out rotamers. So we really sample conformational space in Rosetta. And the way that we determine which conformation, what pose, I'm going to intermix pose and protein, because the pose is what the developers say, and I'm sorry if I say that. But what you see is the conformation is changing, and the reason why Rosetta can get it so well is because of the scoring function. And so I'm going to talk a little bit about the scoring function next. If you know a little bit about how different applications work, MD and Rosetta, MD really uses charm and amber, and these scoring functions are a set of equations that basically depict bonds, angles, dihedrals, van der Waals, and electrostatic interactions. And they do this through a set of equations. They're basically Newtonian equations. And you start from a random force and you plug in the equations and go. And it takes a long time for the force field to calculate, because you're doing advanced things right here. It's not a linear problem. And so that takes time, and it's rather slow. In Rosetta, our scoring function is knowledge base, and simply what that means is that we look at the protein data bank, we look at high-resolution crystal structures, and we pull statistics for them. So for example, how close is a oxygen to a nitrogen? How close is these hydrogen bonding terms? How close are atoms to each other? How close are polar amino acids to each other? and we count how many times this occurs in the protein data bank. And then we basically normalize this count against the distance squared or some other metric. We convert it into a propensity or a probability, and from there we get an energy. And this is how the scoring function in Rosetta works. And just to kind of get an idea, up here I'm just showing a plot of an action center, which is basically the center of charge. And this is for all basic residues against all acidic residues, the center of charge of all basic against acidic residues. So we can see how many times it occurs in the protein data bank. And we see at a distance of 4.1 angstroms, 4.2 angstroms, it occurs often. We convert that into, we normalize it so that we get rid of this trash up here. That basically is just noise. And we can get rid of that, and then we convert it into an energy at the end. And so this is just this is my scoring function right here, and this is a different scoring function. We can convert at a certain distance. We have a certain energy associated between those two residues, or two atom pairs. And this is fast, right? All you have to do is calculate the distance between two atoms and get an energy out of it. Or you have to calculate the angle of atoms. So this occurs very rapidly. And it allows us to search a lot more conformational space. And combined with the rapid search of conformational space and a fairly decent scoring function, we are able to produce all these great papers, all the new enzyme, the designed protein. And that's really the core of what Rosetta is really good at. And to understand, down here I just have, to get the final energy of our protein in molecular mechanics, it's the sum of all these equations. In Rosetta, it's the sum of every term, so van der Waals interaction, hydrogen bonding, I'm going into all of these terms, times a certain weight. And the weight is basically optimized for that type of interaction. And I'm going to go more into detail for this. So the Rosetta scoring function can be basically broken down into two different classes. You have a low resolution scoring function and a high resolution scoring function. And a low resolution scoring function is basically seen in the centroid mode. Represents side chains as centroids, or superatoms. And this low resolution scoring term is found in folding applications, the beginning of docking applications, and several other applications. It's a very, very simple energy function compared to the high resolution scoring function, and it allows us to aggressively search conformational space. So earlier I showed you the global changes, right? This scoring function would help with the global changes. More on the actual side chains and rotamer placements is done in the high resolution. This is a more sophisticated scoring function. It takes a little bit longer to calculate because we're considering all atoms in the protein. And we can sample local residues, and we can sample it fairly fast, not as fast as the low resolution. They share several different qualities about them. In the low resolution scoring term, we have terms specific to them, and then in the high resolution scoring terms, our function, we have specific terms for them, and then they share certain terms. And those are the van der Waals, the solvation, and the electrostatics terms. Those are shared between the two. So I'm just going to go through the low resolution real quick. And in the low resolution scoring term, what we do is we keep the backbone atoms, and then we remove the side chain, and we represent it as a blob, a superatom, just a sphere with density. In Rosetta jargon, I'm going to be switching in between Rosetta jargon and I guess what you see written in the paper because it's hard for me to keep them straight. It's considered a centroid. So often if you have worked with Rosetta, you put in and specifically folding, you say in-file centroid, or in-file full atom. And that's what that means. And the sphere is centered at where the C beta would be. If you're really interested in this on the programming level, at understanding what we're actually doing, you can find the files for the centroid mode in the database chemical residue types centroid. You guys all have this PowerPoint in your PDF, just to let you know. If you have any questions, feel free to ask. Oh, yes.
So for the low resolution, you treat all amino acids the same, right?
Exactly. They have different properties, right? Polar, non-polar, aromatic.
Yeah.
But they are all a superatom. They don't have any side chain information. So in the low resolution scoring term, whenever you score your protein and you look at your protein, you'll see these terms HS pair, SS pair, and sheet. And this really tells you, these terms are for hydrogen bonding in the low resolution. And so what you would have is, if you look at this alpha helix right here and this alpha helix right here, they're kind of incorrectly placed, right? They look weird. This is not completely formed. And the secondary structure pairing term will fix that for us. And what we do is we end up fixing this badly shaped alpha helix and putting it in the correct geometry so that we can get hydrogen bonding between them. And it's controlled through these scoring terms.
So what's HS pair?
Helix strand, secondary structure pair, and then beta sheet. Strand pair, sorry.
It essentially does the same thing as helix strand.
So whenever you're folding proteins, right, if you look at the protein data bank, most proteins are compactly folded. They aren't these long structures. If you do have a long structure, you would turn these modes off in folding. But in general, you have compact structures, right? And the way that we represent this is through the scoring term RG and SynPack. And this only really runs at the beginning of folding. It's not used later on whenever the structure is packed. And what it does is it allows us to start from an extended strand like this, bring it in so that it's folded a little bit, fold it up a little bit more so that it's getting more tight. Now we're really starting to bring the protein together. And then finally, we have the folded protein. At this point, the RG and SynPack would be turned off, and you would now just sample maybe this tail or some minor changes. The radius of gyration of this packing have done its job and now are no longer present, are used as much. And then so those are the low resolution scoring terms. As I said earlier, we share some terms between the high resolution and low resolution scoring terms. But what I'm going to do first is explain how we represent high resolution terms, residues, and then I'm going to go into detail about what are shared between those two. So in the high resolution scoring function, we represent atoms as, or side chains as full atoms. We also have hydrogens placed. And the side chains are represented as these things we call rotamers. And simply what that means is that we don't have one conformation for this amino acid. We have multiple conformations of this amino acid. And full atoms, yes.
Why you need?
What?
Why you don't use just polar hydrogens?
Full hydrogens.
I mean, why you need to all non-polar?
For van der Waals interactions. Right. So if you were to draw a sphere to represent your atoms, and then to draw a hydrogen off of there, it's not going to be perfect spheres. Do you know what I mean? So you can see something like this. This would be your carbon, and then here would be